We call Alpha Centauri our nearest neighbor. If you left for Alpha Centauri today, everyone you have ever loved would be dead before the spacecraft got halfway there. And that's using technology we haven't even built yet. So what does nearest actually mean, and can we ever really get there? If the deep questions of the universe is the kind of thing that lights you up inside, make sure to give this video a like. Now let's get started. Here's something many people don't know about Alpha Centauri. The light hitting your eyes when you look at it tonight left those stars 4.2 years ago, which means you are not seeing Alpha Centauri as it is. You are seeing it as it was, in the past, frozen in transit, arriving late. Everything we observe about that system is already history by the time we receive it. And if anything dramatic happened there today, we wouldn't know for 4 years. That's the universe's ground rule. Information has a speed limit, and it's the same speed limit that makes reaching Alpha Centauri so brutally hard. And here's the part that surprises people. Proxima Centauri will outlive our Sun by an almost incomprehensible margin. Our Sun has roughly 5 billion years left. Proxima has an estimated 4 trillion. It is, in stellar terms, just getting started. In 2016, astronomers confirmed a planet orbiting it, Proxima b, rocky, Earth-sized, sitting in the habitable zone. But what rarely gets mentioned is how they found it, not by seeing it directly, by watching the star wobble. Proxima b's gravity tugs its star ever so slightly as it orbits, and that tiny, almost imperceptible wobble, measured across light years, was enough to reveal an entire world. We found a planet next door by watching a star tremble. Now, I want to be honest with you here. Proxima b is tantalizing, but it comes with enormous uncertainties. Proxima Centauri is a flare star. It regularly blasts its planets with intense bursts of ultraviolet radiation and X-rays, many times more powerful than anything Earth receives from our comparatively gentle Sun. Whether Proxima b has managed to hold on to an atmosphere through billions of years of that bombardment, we genuinely don't know. It may be a world with liquid oceans and a sky full of aurora-lit clouds, or it may be a scorched, airless rock. Science at its best gives us honest uncertainty alongside genuine wonder. And speaking of things that push the limits of what we know, there's another video on this channel that digs into exactly what makes interstellar travel not just difficult, but deeply strange and progressively more terrifying the farther you go. It's on the card above. We explore why interstellar travel gets more terrifying the further you go. If you haven't seen it yet, I'd strongly recommend watching it after this one. The link is in the description and pinned on the comments. But let's come back to the central question. How long would it actually take to get there? The answer depends almost entirely on how fast you're going, and right now, humanity's top speed, our absolute best, is pathetically, heartbreakingly slow by interstellar standards. Voyager 1, as we mentioned, has been traveling since 1977. It moves at roughly 17 kilometers per second. That sounds fast, 17 kilometers every single second. But Alpha Centauri is so far away that at that speed, the journey would take approximately 75,000 years. Not decades, not centuries. 75,000 years. To put that in perspective, 75,000 years ago, modern humans had not yet left Africa. We hadn't painted the cave walls at Lascaux. We hadn't invented writing, agriculture, cities, or mathematics. The entire recorded history of human civilization, every empire, every war, every scientific breakthrough, every work of art, fits comfortably inside a window of time that is less than 1/10 of the journey that Voyager 1 would take to reach the nearest star. New Horizons, the spacecraft that gave us our first close-up images of Pluto back in 2015, travels at roughly 14 kilometers per second. At that pace, the trip would take over 90,000 years. These are the machines we are most proud of. These are our fastest, and against interstellar distances, they are essentially standing still. So why is it so hard to go faster? Why can't we just build a bigger rocket? More thrust, more fuel, more speed. This is where physics steps in and delivers one of its most humbling lessons. The problem with chemical rockets, the kind that have gotten us to the moon, to Mars orbit, to the edge of the solar system, is that they carry their fuel with them. And the more fuel you carry, the heavier the spacecraft. And the heavier the spacecraft, the more fuel you need to accelerate it. And the more fuel you need, the heavier everything gets. It's a vicious, self-defeating spiral that engineers call the Tsiolkovsky rocket equation, and it essentially puts a hard ceiling on how fast chemical propulsion can ever get you. To reach Alpha Centauri in anything resembling a human timeframe, say, a few decades rather than a few geological epochs, you need to be traveling at a significant fraction of the speed of light. We're talking at least 10 to 20%. And the energy required to push even a small spacecraft to those speeds using conventional chemical rockets would exceed anything our civilization could realistically produce. This is not a problem of engineering ambition, it is a problem of fundamental physics. But here's what makes this moment in history so extraordinary, and this is exactly the kind of thing this channel exists to talk about. We are not stuck with chemical rockets. For the first time in human history, we have serious, scientifically grounded proposals for propulsion systems that could actually get something to Alpha Centauri within a human lifetime, not in thousands of years. In decades, they're not ready yet. Some of them are still deeply theoretical, but they are real proposals backed by real physics being explored by real scientists and engineers right now. And in the next part of this video, we're going to start walking through each one, beginning with a concept that is perhaps the most audacious engineering project ever seriously proposed. A laser the size of a small country, firing a beam of pure light at a spacecraft barely heavier than a paperclip, accelerating it to 20% of the speed of light. It sounds like science fiction. It is not. And when we get there, you're going to realize that the dream of reaching another star, the oldest dream our species has ever had, may be closer to reality than any of us imagined. Stay with me. Imagine standing in the Atacama Desert in northern Chile. The sky above you is so clear, so impossibly dark, that the Milky Way casts an actual shadow on the ground. And somewhere out there, on a plateau not far from where you're standing, engineers are assembling something that sounds less like a scientific instrument and more like a weapon from a science fiction novel, a laser array. Enormous, powerful beyond anything ever built before. Designed not to destroy, but to push. This is the heart of an idea called Breakthrough Starshot, and it might be the most serious attempt in human history to actually send something to another star. But before we get into how Breakthrough Starshot works, let's talk about why it was born in the first place, because the backstory matters. In April of 2016, a Russian billionaire named Yuri Milner stood on a stage in New York City alongside Stephen Hawking and announced something that stopped the scientific world in its tracks. He said he was committing $100 million to a research program with a single goal: to develop the technology needed to send a spacecraft to Alpha Centauri within a generation, not within 1,000 years. Within a generation, the room went quiet, because no one had ever said something like that with a straight face and $100 million behind it. Hawking, who spent decades thinking about the long-term future of our species, put it this way, and I'm paraphrasing here, that Earth is a small and fragile world, and we must go to the stars, not because it would be nice to, because it might one day be necessary. So the money was committed, the scientists were assembled, and the question was brutally simple: what is the fastest, most realistic way to get something, anything, to Alpha Centauri in a human lifetime? The answer they landed on was light itself. Here's the core idea behind Breakthrough Starshot, and it is elegantly simple. Even though the engineering is staggeringly complex, light carries momentum. That's not a metaphor, it's a measurable physical fact. When photons, particles of light, bounce off a reflective surface, they transfer a tiny push to that surface. This is called radiation pressure. It's real, it's been measured in laboratories, and it's the foundation of a concept called a light sail, or a laser sail, depending on who you're talking to. The idea is this: you build an incredibly thin, incredibly reflective sail. You attach it to a spacecraft so small it barely deserves the name. A tiny chip, really, carrying a camera, a power source, a communication system, and nothing else. You put this whole system in orbit above Earth, and then you fire a laser at the sail from the ground. Not just any laser, a laser with a combined power output of somewhere around 100 gigawatts. That's roughly the output of 100 nuclear power plants, all focused into a single beam, fired at a sail the size of a child's bedroom. What happens? The photons hit the sail, they push it, and because the spacecraft is so unbelievably light, we're talking grams, not kilograms. The acceleration is extraordinary. Within a matter of minutes, the sail reaches 20% of the speed of light. 20% of the speed of light. At that velocity, the journey to Alpha Centauri takes roughly 20 years. 20 years, not 75,000, not 90,000, 20. Now, before you start celebrating, let's be honest about the challenges, because they are significant. And this channel doesn't skip the hard parts. The first challenge is the sail itself. To work, the sail needs to be extraordinarily thin, thinner than a human hair, and yet strong enough to survive the blast of a 100-gigawatt laser without vaporizing. It needs to be almost perfectly reflective, because any energy it absorbs becomes heat, and even a tiny amount of heat at those power levels would destroy it instantly. For years, this was considered the most difficult material science problem in the entire project. The second challenge is pointing. A laser beam fired from Earth to a sail in orbit needs to stay precisely focused over thousands of kilometers. Any drift, any wobble, and the beam misses the sail or pushes it sideways instead of forward. Achieving that kind of precision is genuinely at the edge of what current optics technology can do. The third challenge is communication. Once that tiny spacecraft is hurtling through interstellar space at 20% of the speed of light, how does it send data back? Its transmitter is the size of a fingernail, and the signal has to travel 4.2 light-years back to Earth. By the time the craft arrives at Proxima Centauri, we'd have to wait 4 more years just to receive the first images. And the fourth challenge, possibly the most overlooked one, is what happens when the sail hits something. At 20% of the speed of light, even a single grain of dust is not a nuisance. It is a catastrophic collision. A single hydrogen atom becomes a high-energy particle capable of damaging the spacecraft's electronics. Interstellar space is mostly empty, yes, but mostly is doing a lot of work in that sentence. So for years after the 2016 announcement, Breakthrough Starshot moved forward slowly. Research teams worked on the sail material problem. Physicists modeled the laser array. Engineers sketched out what the chip-sized spacecraft, they called them star chips, might look like. Progress was real but incremental, and some scientists began to wonder whether the core materials challenge, building a sail that could survive the laser without being destroyed, might simply be too hard with the technology available. Then came 2025, and everything changed. In early 2025, 2 separate research teams, one at Brown University in the United States and one at TU Delft in the Netherlands, published findings that sent a jolt through the interstellar propulsion community. The Brown University team, led by researchers in their engineering and materials science departments, developed a new fabrication method for ultra-thin reflective films using silicon nitride and other materials that are both extremely lightweight and remarkably heat-resistant. The key breakthrough wasn't just the materials themselves. It was the manufacturing process. They found a way to produce these films at a tiny fraction of the cost that had previously been estimated. How much cheaper? Roughly 9,000 times cheaper than earlier projections. 9,000 times. To put that in perspective, a technology that was previously considered economically impossible, the kind of thing that would require the GDP of a small nation just to build enough sail material for a single test mission, suddenly became something that a well-funded research program could realistically pursue. The cost barrier, which many experts had considered the biggest practical obstacle to the entire concept, didn't just come down, it essentially collapsed. Meanwhile, the TU Delft team was working on a complementary problem: the structural integrity of the sail under the extreme conditions of laser acceleration. Using advanced computational modeling and new approaches to nanoscale material engineering, they demonstrated that certain film architectures could survive the kind of brief, intense thermal stress that the laser pulse would generate without cracking, warping, or losing their reflectivity. Together, these two sets of findings didn't just advance the project, they transformed the timeline. What had looked like a technology potentially decades away from even a prototype demonstration suddenly looked like something that could be tested, actually tested, not just theorized, within the next 10 to 15 years. And here's why that matters far beyond the science itself, because what Breakthrough Starshot represents isn't just a mission to Alpha Centauri. It's a proof of concept. It's humanity saying, for the very first time, not one day we might reach the stars, but here is a specific design, here are the engineering requirements, here is a cost estimate, and here is a timeline. That shift from inspiration to engineering is one of the most significant transitions in the history of space exploration, and most people have absolutely no idea it's happening. But Breakthrough Starshot isn't the only game in town, not even close, and some of the alternative approaches are arguably even more ambitious, and in some ways more realistic for carrying humans rather than chips. Because here's the thing the Starshot concept quietly sidesteps: it can send information to Alpha Centauri, it can send cameras, sensors, and maybe even basic scientific instruments. What it cannot do, not even remotely, not even theoretically with current physics, is slow down a spacecraft traveling at 20% of the speed of light with no braking mechanism will zip through the Alpha Centauri system in a matter of hours. Hours. It'll have a brief window to capture data, fire a signal back toward Earth, and then it'll be gone, disappearing into the dark between galaxies. If we ever want to actually stop at another star, to orbit it, to study its planets up close, to land on one of them, we need something fundamentally different. And in the next part of this video, we're going to talk about what that might look like. We're going to explore nuclear propulsion, not the kind of nuclear energy you put in a power plant, but something far more raw and far more powerful. We're going to talk about Project Orion, the classified Cold War program that genuinely proposed detonating nuclear bombs behind a spacecraft to push it through space. And we're going to look at where that concept has evolved in the decades since, into designs that some physicists believe could carry not just instruments, but human beings to another star. Because the question was never just, can we send something to Alpha Centauri? The question is, can we go there? Is 1958. The Cold War is at its peak. The United States and the Soviet Union are locked in a race, not just for missiles and bombs, but for the stars themselves. NASA has just been founded. Sputnik has been in orbit for less than a year. And in a classified government facility in California, a group of some of the most brilliant physicists in the world are quietly working on a plan so audacious, so borderline insane, that when you first hear it, your instinct is to laugh. Their plan was to build a spacecraft the size of an ocean liner, load it with thousands of nuclear bombs, and then detonate those bombs, one after another, behind the ship, using the shockwaves to push it through space at speeds no chemical rocket could ever dream of. They called it Project Orion, and it was completely, mathematically, physically real. The man at the center of it was a physicist named Freeman Dyson, one of the most original scientific minds of the 20th century. Dyson wasn't a fringe thinker or a science fiction dreamer. He was a rigorous, methodical, deeply serious scientist. And when he ran the numbers on Project Orion, what he found was genuinely staggering. A nuclear pulse drive, which is the technical name for what Orion was doing, could, in theory, accelerate a massive spacecraft to roughly 3 to 5% of the speed of light. At 3% of the speed of light, the journey to Alpha Centauri would take somewhere between 80 and 140 years, still multiple human lifetimes. But compared to 75,000 years, it's a revolution, and Dyson didn't stop there. He calculated that with a truly large Orion vehicle, one carrying enough bombs and designed for maximum efficiency, speeds approaching 10% of the speed of light might be achievable. At 10% light speed, you're looking at roughly 40 to 50 years to Alpha Centauri, within a single human lifetime. On a ship large enough to carry a crew, the physics worked, the math checked out. So what happened? Politics happened. And one treaty, in 1963, the United States and the Soviet Union signed the Partial Nuclear Test Ban Treaty, which prohibited the detonation of nuclear weapons in space. With a single stroke of a pen, Project Orion became illegal. The program was quietly cancelled, the documents were classified, and one of the most genuinely promising interstellar propulsion concepts ever devised was shelved. Not because it didn't work, but because the world had decided it was too dangerous to test. Freeman Dyson later said it was one of the greatest tragedies in the history of space exploration. Not the cancellation itself. He understood the political reality, but the fact that humanity had a real path to the stars in its hands and chose not to walk it. The classified files on Project Orion weren't fully declassified until the 1990s, and when researchers finally got to read through the original engineering documents, the reaction in the astrophysics community was a mix of awe and genuine grief, because the people who designed Orion weren't just dreaming, they were engineering, they had solved problems, they had found real answers, and those answers were buried for 30 years. But here's what's important to understand. The core idea behind Orion, using nuclear energy to propel a spacecraft, didn't die with the project. It evolved. And in the decades since, physicists and engineers have developed increasingly sophisticated versions of nuclear propulsion that sidestep the political problems of detonating actual bombs while still harnessing the extraordinary energy density that nuclear reactions provide. Let's talk about what that actually means, because nuclear propulsion covers a wide spectrum of concepts, and they are not all created equal. The simplest version is called nuclear thermal propulsion. Instead of exploding bombs, you use a nuclear reactor to superheat a propellant, usually hydrogen, and expel it through a nozzle. NASA actually tested nuclear thermal rocket engines in the 1960s and 70s under a program called NERVA. They worked. They produced thrust roughly twice as efficient as the best chemical rockets. And a modernized version of this technology could cut the travel time to Mars from 7 or 8 months to roughly 3 or 4. For Mars, nuclear thermal propulsion is genuinely exciting. For Alpha Centauri, it's nowhere near enough. At the speeds nuclear thermal rockets can achieve, the journey would still take thousands of years, better than chemical, still nowhere near interstellar. The next step up the energy ladder is nuclear pulse propulsion, the direct descendant of Project Orion. Modern versions of this concept don't use crude hydrogen bombs. They use precisely engineered microfusion explosions, tiny controlled bursts of fusion energy, each one small and precise enough to be practical while still delivering enormous thrust. The most developed modern version of this idea was a concept called Project Daedalus, designed by the British Interplanetary Society in the 1970s. Daedalus wasn't a vague sketch. It was a detailed engineering study that ran for 5 years and produced a 500-page technical report. The spacecraft they designed was enormous, nearly 200 meters long, heavier than the Eiffel Tower, and it would use small pellets of deuterium and helium-3 ignited by electron beams to produce fusion micro-explosions at a rate of 250 per second. The projected top speed for Daedalus, 12% of the speed of light. At 12% light speed, the trip to Alpha Centauri takes roughly 36 years. Daedalus had one fatal flaw, though the same one we noted with Breakthrough Starshot. It had no braking system. It was designed as a flyby mission. It would zip through the Alpha Centauri system at 12% of light speed, spending only a few days in the vicinity of the stars before sailing on into the void forever. So in the 1980s and 90s, the British Interplanetary Society went back to the drawing board and began work on a follow-up study called Project Longshot, and later Project Icarus, specifically designed to address the deceleration problem. Because, if we're being serious about interstellar travel, a flyby isn't enough. We need a ship that can actually stop. And stopping is, in many ways, harder than accelerating. To decelerate from 12% of the speed of light, you need to carry enough propellant to push against your own momentum, which means carrying far more fuel, which means the ship has to be bigger and heavier, which means you need even more fuel to accelerate it in the first place. It's the same vicious spiral as chemical rockets, just at a far higher energy level. Several solutions have been proposed over the years. One is to use the destination star's own radiation pressure as a brake, essentially deploying a giant reflective sail as you approach Proxima Centauri and letting the star's light push against you from the front, slowing you down. Another is to use a magnetic scoop, a device that collects the thin wisps of interstellar hydrogen as the spacecraft moves through space and uses them both as fuel and as braking mass. A third is to carry dedicated deceleration propellant and simply accept the enormous weight penalty that comes with it. None of these solutions are simple. All of them add complexity, mass, and cost to an already extraordinarily complex mission, but none of them violate known physics. They are engineering challenges, not scientific impossibilities. And then there's fusion, pure fusion propulsion, not the pulse detonation approach of Daedalus, but a sustained, continuous fusion burn, is considered by many physicists to be the single most promising pathway to crewed interstellar flight. And in the last decade, fusion has gone from a perpetually out-of-reach goal. The running joke was always that commercial fusion power is 30 years away and always will be, to something that feels, for the first time, genuinely close. In December of 2022, the National Ignition Facility at Lawrence Livermore National Laboratory in California achieved something that had never been done before in human history. For the first time, a fusion experiment produced more energy than the lasers put into it. Ignition, the holy grail of fusion research, was achieved. It was a single experiment under very specific conditions, and it's a long road from that moment to a functional fusion reactor, let alone a fusion rocket engine. But the significance of what happened in that room on that day is almost impossible to overstate. It was proof that the physics works, that humanity can, in principle, harness the same process that powers the sun. Fusion rockets, if they can be built, could achieve speeds of 5 to 10% of the speed of light with realistic fuel loads. Combined with a braking strategy, this puts a crewed mission to Alpha Centauri within the range of roughly 50 to 100 years. Not a human lifetime, but within the span of 2 or 3 generations. Which brings us to one of the most profound and emotionally complex questions in the entire field of interstellar exploration. If the journey takes longer than a human lifetime, if the people who launch the ship will never see the destination, who goes? And more importantly, why would they? This is where interstellar travel stops being a physics problem and becomes a philosophical one. It becomes a question about what human beings value, what we're willing to sacrifice, and what kind of future we want to build. The concept of a generation ship, a vessel large enough and self-sufficient enough to sustain a human population across multiple generations of travel, has been discussed by serious scientists and philosophers for nearly a century. And in the next part of this video, we're going to go deep on exactly that. What would a generation ship actually look like? How large does it need to be? How do you keep a population genetically healthy across centuries of isolation? What happens to the culture, the identity, the psychological well-being of people who are born in the void between stars? Because the math of getting there is only half the story, the other half is the human one. And it is, without question, the harder problem. If you are enjoying this journey, make sure to subscribe to the channel. Every video on this channel is designed to give you that rare combination of scientific accuracy and genuine awe. Picture this: you are born on a ship. Not born near a ship, not born in a city with a view of a launch pad, born on one. The walls around you are metal, the sky above you is a ceiling. The sun you've heard about in stories is a faint point of light in a camera feed. Already so distant it looks like just another star. You will never feel wind on your face, you will never stand on soil. You will grow up, fall in love, have children of your own, grow old, and die, all inside a vessel moving through a darkness so complete and so vast that the human mind was never designed to truly comprehend it. And somewhere in that same ship, in a room you've probably never visited, there is a navigation system quietly counting down the centuries. This is the reality of a generation ship, not a fantasy, not a thought experiment. A genuine engineering and sociological challenge that some of the world's most serious scientists are working on right now. Because if fusion rockets take 100 years to reach Alpha Centauri, and if antimatter, which we'll get to, is still centuries away from being practical, then a generation ship might be the most realistic vehicle for getting human beings to another star. And the more you look at what that actually requires, the more extraordinary the challenge becomes. Let's start with the numbers. Because the numbers, as always, tell the real story. Geneticists who study isolated human populations have estimated that to maintain a healthy gene pool across centuries of travel, to prevent the kind of inbreeding and genetic bottlenecking that has devastated isolated communities throughout human history, you need a minimum founding population of somewhere between 10,000 and 40,000 people. Not 100, not 1,000, 10,000 at minimum, 10,000 people living inside a spacecraft. Now think about what 10,000 people need. They need food, which means agriculture, which means either vast growing spaces lit by artificial sunlight or sophisticated hydroponic systems capable of feeding a small city. They need water, which means closed-loop recycling systems so efficient that not a single molecule is wasted. They need air, which means biological systems, plants, algae, bacteria, maintaining an atmosphere in perfect balance for centuries without a single catastrophic failure. They need medicine, education, governance, justice systems, ways to resolve conflict without the option of leaving because there is nowhere to go. They need art and music and sport and all the things that keep human beings sane and connected and alive in ways that go beyond mere biology. And they need all of this to function reliably, not for a decade, not for a generation, but for 100 years, or 200, or more, with no possibility of resupply, no possibility of outside help, no mission control on Earth that can do anything more than send a radio message that takes 4 years to arrive. The engineering challenges alone are staggering. The life support systems on the International Space Station, which houses 6 people, require constant maintenance by highly trained astronauts and remote support from thousands of engineers on the ground. And the ISS has been continuously occupied for only about 25 years. A generation ship carrying 10,000 people would need life support systems 1,000 times more complex, running 100 times longer with no external support whatsoever. Every critical system would need to be not just redundant, but multiply redundant. The backup would need a backup. The backup's backup would need a backup. And every component in every system would need to be either replaceable using materials available on the ship or repairable by people trained aboard the ship, which means the ship doesn't just need engineers. It needs a self-sustaining educational system capable of training engineers for as long as the journey lasts. Some researchers have proposed that the ship would essentially need to be a small civilization, not a vessel with passengers, but a world with citizens, a world that happens to be moving. The physicist and science communicator Frédéric Marin has done some of the most detailed computational modeling of generation ship populations ever published. His simulations, run using a program called Heritage, model the genetic and demographic evolution of small isolated populations over interstellar journey timescales. His findings were both illuminating and sobering. Even with careful management of reproduction and genetic diversity, the populations in his models experienced significant challenges over timescales of multiple centuries. Maintaining genetic health turns out to require not just a large initial population, but active, ongoing management of who has children with whom, a level of social control that raises profound ethical questions. And that's where the science hands the problem off to philosophy, because even if you could build the ship, even if you could solve the engineering, the genetics, the agriculture, the medicine, you'd still face what many scholars consider the deepest problem of all. Is it ethical to create a generation ship in the first place? Think about what you are actually doing when you launch one. The people who make the decision to go, the founders, the first generation, are choosing voluntarily. They understand what they're signing up for. But every person born on that ship after the launch has made no such choice. They are born into a journey they did not agree to, toward a destination they will never see, in a world they can never leave. The philosopher and bioethicist Konrad Socik has written extensively about this problem. He calls it the problem of the people of the ship. The idea that the generations born in transit have a fundamentally different moral status than the generation that launched. They are, in a very real sense, citizens of a nation that never existed on any map, defined entirely by a mission they inherited rather than chose. Some thinkers argue this is no different from being born into any particular culture, country, or religion. None of us choose the circumstances of our birth, and yet we find meaning within them. Others argue that the degree of constraint aboard an interstellar vessel is so far beyond anything experienced in normal human life that the comparison breaks down entirely. There are no easy answers here. But the fact that serious ethicists and philosophers are wrestling with these questions, not as abstractions, but as practical considerations for real mission planning, tells you something important about where interstellar travel research actually is right now. Beyond the ethical questions, there is the psychological one. And this might be the most underappreciated challenge of all. Human beings evolved on a planet. Our minds were shaped by open skies, by seasons, by the experience of having a horizon. We are deep, fundamentally terrestrial creatures. And everything we know about long-duration isolation, from Antarctic research stations, from submarine deployments, from the psychological literature on prisoners in solitary confinement, tells us that prolonged confinement in a closed, unchanging environment has profound effects on the human mind. Depression, anxiety, interpersonal conflict that escalates in the absence of any escape valve. A phenomenon psychologists call third quarter syndrome, a sharp drop in morale and mental health that occurs roughly 3/4 of the way through a long isolated mission, when the end feels simultaneously close and impossibly far. Now imagine not months of this, but years, decades, an entire lifetime. Researchers studying the psychological requirements of a generation ship have concluded that the vessel would need not just physical spaces designed for well-being, parks, open areas, spaces that simulate the experience of being outdoors, but also sophisticated psychological support systems, community structures, and possibly even carefully designed narratives of meaning and purpose that help people feel connected to a mission larger than their own individual lives. In other words, the generation ship would need a culture, a shared story, a reason that felt true, not just to the founders, but to their grandchildren and great-grandchildren. And here's where something fascinating happens. Because when you study the history of long migrations, of groups of human beings who traveled vast distances over long periods of time, driven by the need to find new homes, you find that the most successful ones shared certain characteristics. They had strong social cohesion, they had shared purpose, they had rituals and stories that connected each generation to the ones before and after. They had, in a word, culture, and that culture was the survival mechanism. Some researchers studying interstellar generation ships have begun arguing that the design of the ship's culture, the stories it tells about itself, the values it transmits from one generation to the next, the way it handles conflict and grief and celebration, may be just as important to mission success as the engineering of its life support systems. Because a ship with perfect recyclers and failing morale will still fail. A ship with imperfect systems and a community strong enough to solve problems together might actually make it. Now here's the part that should make your mind spark, because all of this, the engineering, the ethics, the psychology, the culture, all of it assumes that the journey takes a very long time, that we are stuck for the foreseeable future with the limitation of speed. But what if we're not? What if there are approaches to interstellar travel that don't require generation ships at all, because they could, in principle, get a crew to Alpha Centauri within a single human lifetime? What if the physics that governs the universe contains a kind of hidden shortcut, not science fiction, but real mathematics? That changes the entire picture. In the next part of this video, we're going to leave the realm of near-future engineering and step into something wilder. We're going to talk about antimatter, the most energy-dense fuel physically possible, the stuff that causes total annihilation on contact with normal matter. We're going to talk about what an antimatter rocket could actually do, and we're going to begin exploring one of the most breathtaking and controversial ideas in all of theoretical physics, the Alcubierre warp drive, a concept that is not dismissed by serious physicists, but is instead taken seriously enough to have been the subject of real research programs inside NASA itself. The universe, it turns out, may have left us a few doors. We just haven't figured out how to open them yet. Stay with me. There is a substance so reactive, so extraordinarily energetic that a single gram of it, 1 gram, less than the weight of a paperclip, contains the equivalent energy of a nuclear bomb. When it comes into contact with ordinary matter, both are completely destroyed. Not burned, not split apart, annihilated, converted entirely into pure energy with 100% efficiency, No waste, no exhaust, no byproduct except raw blinding radiation. That substance is antimatter, and it is not science fiction. It is made in particle accelerators right now, today, at facilities like CERN in Switzerland. Physicists create it, study it, and store it in magnetic traps that keep it suspended in a vacuum so it never touches the walls of its container and destroys itself prematurely. Antimatter is the most energy-dense fuel that physics, not engineering, not technology, but the fundamental laws of the universe permits to exist. And some researchers believe it is the key to reaching Alpha Centauri within a human lifetime. Let's understand exactly why antimatter is so extraordinary, because the numbers are almost offensive compared to everything else we've discussed. Chemical rockets, the kind that launch satellites and crew capsules today, convert roughly 0.3% of their fuel mass into usable energy. Nuclear fission reactors, the kind that power submarines and generate electricity, convert roughly 0.1% of fuel mass into energy. Nuclear fusion, the process we talked about in the last section, the one that powers the sun, converts roughly 0.7% of fuel mass into energy. Antimatter annihilation converts 100%. Every single atom of fuel becomes pure energy. Nothing is wasted. To put that in terms of raw performance, a fusion rocket might achieve speeds of 5 to 10% of the speed of light with a realistic fuel load. An antimatter rocket, using the same mass ratio of fuel to spacecraft, could theoretically reach speeds of 70 to 80% of the speed of light. At 70% of light speed, the journey to Alpha Centauri takes roughly 6 years, on a single crewed spacecraft with a living crew that boards the ship on Earth and steps off near Proxima Centauri before they turn 40. That's not a generation ship. That's not a flyby chip. That is human interstellar travel in the most profound and complete sense of those words. So why aren't we building one? The answer is heartbreaking in its simplicity. We can make antimatter. We just cannot make enough of it, not even remotely close to enough. The largest antimatter production facility on Earth is at CERN, home of the Large Hadron Collider. CERN produces roughly 10 to 15 nanograms of antiprotons per year. A nanogram is 1/1000th of a gram, so in a full year of operation, the most powerful particle physics laboratory in human history produces a quantity of antimatter that you could not see with the naked eye. An antimatter rocket capable of reaching Alpha Centauri would need somewhere in the range of tens of grams to hundreds of kilograms of antimatter, depending on the ship's design and the desired speed. At current production rates, manufacturing that much antimatter would take millions of years, millions. And it's not just a question of building bigger accelerators. The production of antimatter is inherently inefficient. It takes vastly more energy to create antimatter than you get back when you use it. Right now, the energy return ratio is roughly 1 to 10 billion. For every 10 billion units of energy you put into a particle accelerator, you get 1 unit worth of antimatter out. Until that ratio improves by many orders of magnitude, antimatter propulsion remains an extraordinary theoretical capability locked behind an equally extraordinary practical barrier. But here's why you shouldn't dismiss it entirely. Because the history of energy technology is a history of impossible things becoming possible. 40 years before the first nuclear reactor went critical, the idea that you could split an atom and release energy was considered fringe physics. 30 years before the first transistor, the idea of fitting 1 billion switches onto a chip the size of your fingernail would have seemed like madness. The barriers that exist today are real, but they are engineering and economics barriers, not physics barriers. Antimatter exists. Antimatter annihilation works exactly as the equations predict. The question is whether human ingenuity can find a path from where we are to where we need to be. Some researchers are working on entirely new approaches to antimatter production methods that don't rely on brute force particle acceleration, but instead on more elegant quantum processes. Others are exploring whether naturally occurring concentrations of antimatter might exist in certain astrophysical environments that could theoretically be harvested. These ideas are speculative, but they are being taken seriously by serious people. And in physics, serious speculation has a way of becoming engineering reality faster than anyone expects. But antimatter, for all its extraordinary promise, is still fundamentally a conventional propulsion system. You burn fuel, you generate thrust, you move through space the normal way, just faster than anything we've ever built before. What if moving through space the normal way is the wrong approach entirely? What if, instead of pushing a spacecraft through the fabric of space-time, you could push the fabric itself? This is the idea at the heart of the Alcubierre warp drive. And before you roll your eyes and think of starships on a television screen, I want you to understand something clearly. This concept was not invented by a screenwriter. It was published in a peer-reviewed physics journal in 1994 by a Mexican theoretical physicist named Miguel Alcubierre, and the paper is grounded in the same mathematical framework, Einstein's general theory of relativity, that underlies GPS satellites, gravitational wave detectors, and black hole imaging. The Alcubierre drive is not science fiction dressed up in equations. It is a genuine mathematical solution to Einstein's field equations. It is real physics. And understanding why it is both revolutionary and deeply problematic tells you something profound about the universe we live in. Here is the core idea. Einstein's general relativity tells us that space-time, the four-dimensional fabric of the universe, is not a rigid, fixed stage on which events happen. It is a dynamic, flexible structure that can be curved, stretched, compressed, and warped by mass and energy. We see this in everyday reality. The GPS satellites orbiting Earth have to account for the curvature of space-time caused by Earth's gravity, or they would give you wrong directions within minutes. Gravitational waves, ripples in space-time itself, were detected for the first time in 2015, created by two black holes colliding over 1 billion light-years away. Space-time bends, space-time flexes. That is not a metaphor, that is measured, verified, experimental fact. What Alcubierre realized that if space-time can be curved by mass and energy, then, in principle, it could be curved in a very specific and deliberate way. Imagine compressing space-time in front of a spacecraft, making the space ahead of it smaller, shorter, closer, while simultaneously expanding space-time behind the spacecraft, stretching it out. The spacecraft itself would sit inside a bubble of flat, normal space-time. It would not move through space in the conventional sense. Instead, space itself would move around it, carrying it forward the way a wave carries a surfer. The extraordinary thing about this mechanism is that it sidesteps the fundamental speed limit of the universe. Einstein's special relativity tells us that nothing with mass can accelerate to the speed of light. The energy required becomes infinite as you approach it. But that rule applies to objects moving through space-time. It says nothing about space-time itself moving. There is no known speed limit on how fast space can expand or contract. We know, in fact, that during the period of cosmic inflation in the very early universe, regions of space were separating from each other faster than the speed of light. The universe itself does not obey the speed limit it imposes on everything inside it. An Alcubierre bubble, if it could be created, would allow a spacecraft to travel between any 2 points in the universe in any amount of time, even less time than light would take to cover the same distance, without ever locally exceeding the speed of light inside the bubble. It is genuinely a warp drive. The mathematics says so, but, and this is a significant but, the mathematics also reveals the problems, and they are severe. The first problem is energy. To create and maintain an Alcubierre bubble large enough to contain a spacecraft, The original 1994 calculations estimated that you would need an amount of exotic energy roughly equivalent to the total mass energy of the planet Jupiter. Not the energy you could get from converting Jupiter into fuel, the mass energy of an entire planet used all at once to warp a bubble a few meters across. The second problem is the nature of that energy. It cannot be ordinary energy. It has to be what physicists call exotic matter, a hypothetical form of matter with negative energy density. Negative energy is not antimatter. It is something stranger, a form of matter or energy that has never been directly observed, though quantum mechanics suggests it might exist under very specific conditions in the form of what's called the Casimir effect. The third problem is control. Even if you could create an Alcubierre bubble, the physics suggests that nothing inside the bubble could send a signal to the front of it, which means the crew would have no way to steer or stop the drive from the inside. For years after Alcubierre's original paper, most physicists treated the concept as a fascinating mathematical curiosity, real in the sense that the equations allowed it, but completely impractical in any engineering sense because of the exotic matter requirement. Then, in 2012, a NASA physicist named Harold Sonny White announced something that sent a jolt through the theoretical propulsion community. Working at NASA's Johnson Space Center as part of a program called the EagleWorks Laboratories, a small, officially sanctioned research group dedicated to exploring speculative but physics-based propulsion concepts. White recalculated the energy requirements of the Alcubierre drive using a modified bubble geometry. His finding was that by changing the shape of the warp bubble from a simple sphere to a more complex, oscillating toroidal form, the energy requirement could be reduced dramatically. Not from Jupiter mass energy to a reasonable amount, but from Jupiter mass energy to something closer to the mass energy of a small spacecraft. Still extraordinary, still far beyond anything we can produce today, but reduced by many orders of magnitude. White's calculations were controversial. Other physicists pointed out significant assumptions in his model, but they were taken seriously enough that NASA allowed him to continue the research. And in 2021, a separate team of physicists published a paper describing what they called a positive energy warp drive, a modified version of the Alcubierre concept that might not require exotic negative energy matter at all. Relying instead on configurations of ordinary matter and energy fields, the debate continues. The problems are real and unresolved, but the conversation is happening in peer-reviewed journals, in physics departments, in NASA research programs. That alone tells you something remarkable about where human thinking on interstellar travel has arrived. Because here is the deeper truth underneath all of this, underneath the laser sails and the fusion rockets and the antimatter drives and the warp bubbles. The universe is under no obligation to make itself easy for us to navigate. The speed of light is not a suggestion. The distances between stars are not a mistake. They are features of a cosmos that existed for nearly 14 billion years before we arrived, and will exist for trillions of years after we're gone. And yet, here we are, a species that crawled out of the ocean, learned to make fire, invented mathematics, split the atom, landed on the moon, and is now seriously, rigorously, scientifically discussing how to cross 4.2 light-years of interstellar void. Not if, how. In the next part of this video, we're going to zoom back out and look at the big picture of where all these technologies stand today, what's closest to reality, what the actual timeline might look like, and what a serious roadmap to Alpha Centauri could plausibly resemble given everything we currently know. Because the honest answer to the question, how long would it take to reach Alpha Centauri, isn't a single number. It's a spectrum ranging from 20 years with a chip-sized probe to potentially never with a crewed ship, depending on which technologies succeed and which ones don't. And the line between those outcomes is being drawn right now by researchers working in laboratories, by engineers running simulations, by physicists scribbling equations at midnight, by people like the ones who are watching this video and asking exactly this kind of question. Let's take a breath. Over the last 5 parts, we've covered an enormous amount of ground. We've talked about the sheer scale of the distance to Alpha Centauri, 41 trillion kilometers of cold, silent void. We've talked about the spacecraft we have right now, crawling through the outer solar system at speeds that would take them 75,000 years to reach the nearest star. We've talked about laser sails and nuclear bombs and fusion rockets and antimatter and a warp bubble dreamed up by a Mexican physicist that lives inside Einstein's equations like a hidden door. And if you've been paying attention, really paying attention, you've probably noticed something. Every single technology we've discussed carries with it a but, a caveat, a wall that the current state of human capability hasn't yet climbed over. Breakthrough Starshot is real, but the laser array doesn't exist yet, and the sail material was only proven manufacturable at scale in 2025. Nuclear pulse propulsion works mathematically, but we banned the bombs needed to test it 60 years ago. And no one has seriously proposed reviving that program. Fusion rockets are suddenly more plausible than they've ever been, but we haven't built a sustained fusion reactor yet, let alone one compact and powerful enough to fit inside a spacecraft. Antimatter is the perfect fuel, but we produce nanograms of it per year when we'd need kilograms. The Alcubierre drive is genuine physics, but it requires either exotic matter that may not exist in usable form or energy densities we have no idea how to achieve. Breakthrough Starshot succeeds in the mid-2000s and sends back images of Proxima b. Those images show something, an atmosphere perhaps, or a chemical signature that shouldn't be there if the planet is lifeless. That finding transforms the political and financial will behind interstellar missions overnight. Suddenly, a nuclear or fusion probe to go deeper, to orbit, to study becomes not a dream but a mandate. The probe mission takes another century. It confirms what the images hinted at. And now, the conversation about a crewed mission stops being theoretical and becomes the defining project of human civilization. This is how exploration actually works. Not in a single bold leap, but in a sequence of smaller steps, each one made possible by the one before, each one raising the stakes for the next. And there is one more factor that belongs in any honest discussion of interstellar travel timelines, one that makes all these projections simultaneously more uncertain and more exciting. It is the factor of artificial intelligence and its role in spacecraft design, mission planning, and potentially in the crews of future interstellar vessels themselves. Right now, AI systems are contributing to everything from materials discovery, helping identify new compounds for laser sail films, to orbital mechanics calculations, to the design of closed-loop life support systems. As AI capabilities continue to develop, the pace at which we can iterate through engineering challenges and identify viable solutions is likely to accelerate dramatically. Some researchers have proposed that the first interstellar mission might not carry biological humans at all, but artificial minds. Digital consciousnesses, if such a thing becomes possible, that could survive the journey indefinitely, require no food or water or air, and experience the passage of time in whatever way they are designed to experience it. They could conduct the entire scientific mission at Proxima Centauri and transmit every observation back to Earth, not as a replacement for human exploration, but as a forerunner, an advance party. Whether digital consciousness is possible is a question that sits at the intersection of neuroscience, philosophy, and computer science, and it is nowhere near resolved, but it is being discussed. And a generation ago, it wasn't even being discussed seriously. There is a pattern running through everything, we've talked about in this video. Do you see it? Every technology we've explored, every propulsion system, every life support concept, every navigation approach began as something that was considered impossible or at best wildly impractical, and then became first theoretically possible, then practically conceivable, then actually achievable. Chemical rockets were a fantasy until they weren't. Nuclear reactors were theoretical until they were built. GPS was a dream until it became something you use to find a coffee shop. The pattern is consistent, the timeline is unpredictable, but the direction has always been the same: forward. And in the next part of this video, we're going to take that forward momentum and apply it to the most profound question buried inside everything we've been discussing. Not just how long would it take to reach Alpha Centauri, but what would we actually find when we got there? Because Proxima b, the rocky planet orbiting Proxima Centauri in the habitable zone, is not just an astronomical data point, it is a world. And the question of what kind of world it is, whether it has an atmosphere, whether it has liquid water, whether it has life, is one of the most electrifying open questions in all of science right now. Because if the answer turns out to be yes, if there is something alive on that planet, even something microscopic, then every calculation we've done about timelines and technologies becomes infinitely more urgent, and the stars stop feeling quite so far away. If you're still watching, the universe has its hooks in you, and this channel was made exactly for that. Don't forget to subscribe and give this a like. Every video we go somewhere new and come back seeing a little more than we did before. In 1950, the physicist Enrico Fermi sat down to lunch with a group of colleagues at Los Alamos National Laboratory in New Mexico. The conversation drifted, as it sometimes does among physicists, toward the universe and the possibility of other civilizations out there among the stars. And somewhere between the main course and dessert, Fermi asked a question so simple and so devastating that it has never fully been answered in the 75 years since. Where is everybody? That's it. That was the question. 3 words. Where is everybody? Because here is the paradox at the heart of it. The universe is roughly 13.8 billion years old. It contains somewhere between 200 billion and 2 trillion galaxies, each holding hundreds of billions of stars. A significant fraction of those stars have planets. A significant fraction of those planets are rocky. A significant fraction of those rocky planets orbit in habitable zones. Even if only a tiny percentage of habitable planets actually develop life, and an even tinier percentage of that life develops intelligence, the sheer scale of the numbers suggests that the universe should be absolutely teeming with civilizations, some of them billions of years more advanced than us. And yet, silence. The sky is quiet, no signals, no megastructures visible in distant star systems, no alien probes in our solar system, no transmissions in any frequency we've searched, nothing. That is the Fermi paradox. And it is one of the most profound unsolved problems in all of science. Now, you might be wondering why we're talking about the Fermi paradox is in a video about traveling to Alpha Centauri. The connection is deeper than it might first appear, because the Fermi paradox isn't just an abstract puzzle about alien life. It is a mirror held up to our own future. It forces us to ask, what happens to civilizations that develop the kind of technology we've been discussing? Laser sails, fusion rockets, antimatter drives. Do they use it? Do they spread across their galaxy? Do they survive long enough to try? The answers to those questions have direct, immediate implications for what the Alpha Centauri mission actually means for humanity, not just scientifically, existentially. Let's walk through the major proposed resolutions to the Fermi paradox, because they are not all equally comforting, and some of them are deeply, genuinely unsettling. The first and most optimistic resolution is simply that we haven't looked hard enough. The universe is incomprehensibly large. The frequencies on which civilizations might communicate are effectively infinite. The time we've spent actively searching since the first serious SETI effort in 1960 is a tiny fraction of a cosmic eye blink. Maybe the signals are there, and we just haven't pointed our instruments in the right direction at the right moment. This is plausible, it is reassuring, and it may well be true. But it gets harder to sustain as our searches become more comprehensive and the silence continues. The second resolution is the rare Earth hypothesis, the idea that the conditions that produced life on Earth, and particularly complex intelligent life, are so extraordinarily specific and improbable that they may have occurred only once, or very rarely, in the observable universe. The precise mass of our Sun, the stabilizing influence of our unusually large moon, the presence of Jupiter acting as a gravitational shield that deflects many large asteroids away from the inner solar system, the plate tectonics that regulate our climate over geological timescales. Strip away any one of these factors and the story of life on Earth might have ended before it really began. If the rare Earth hypothesis is correct, it means we may be alone or nearly alone in the galaxy, which is both awe-inspiring and deeply lonely. And it makes the project of reaching other stars feel less like making contact and more like carrying something precious and irreplaceable outward into the dark. The third resolution, and this is the one that keeps some scientists awake at night, is called the Great Filter. The idea, developed by economist Robin Hanson in 1998, goes like this. Among the many steps required to go from a lifeless planet to a spacefaring civilization, from simple chemistry to single-celled life, to multicellular organisms, to intelligence, to technology, to interstellar capability, there must be at least one step that is extraordinarily, almost impossibly difficult. A filter, a barrier, something that almost no civilization gets past. The question is, where is that filter? Is it behind us or ahead of us? If it's behind us, if the incredibly hard step was something in our past, like the origin of life itself, or the development of the eukaryotic cell, or the emergence of sexual reproduction, then we are among the rare few who made it through. The galaxy may be littered with planets that got stuck at some early stage of biological complexity and never progressed further. We are the lucky exceptions. But if the Great Filter is ahead of us, if it's something that virtually every civilization encounters after reaching our current stage of development and fails to survive, then the silence of the universe takes on an entirely different meaning. It becomes a warning. What could that filter be? Nuclear war, engineered pandemics, climate catastrophe severe enough to collapse civilization, artificial intelligence that escapes human control, the development of some weapon or technology so powerful and so accessible that any sufficiently advanced civilization inevitably destroys itself before it ever reaches the stars. Here is why this matters for interstellar travel. If the Great Filter is ahead of us, if the pattern of the universe is that civilizations develop the capacity for interstellar travel and then disappear before using it, then our attempts to reach Alpha Centauri are not just a scientific project, they are a test of whether we are the first civilization in the history of this galaxy to get past the filter, to survive our own technology long enough to actually leave. Carl Sagan, who spent much of his life thinking about this exact question, believed that the development of interstellar capability and the achievement of genuine civilizational maturity were essentially the same thing. That a species sophisticated enough to cross the void between stars would necessarily have solved the problems, the wars, the tribalism, the short-term thinking that threatened civilizations at earlier stages. That getting to the stars and surviving as a species were not two separate goals, but a single, unified one. Whether he was right, we don't yet know. But there is something in that idea that feels important. Something that makes the project of reaching Alpha Centauri feel less like a technical challenge and more like a moral one. Now let's talk about the human reason, the one underneath all the science and all the philosophy. Why do we want to go to Alpha Centauri? Not the official answer, not to expand humanity's presence in the universe, or to search for potentially habitable worlds, or to advance our scientific understanding. Those answers are true, but they are not the deepest true answer. The deepest true answer is something more like this. We go because we have always gone, because the impulse to cross the next horizon, to see what is on the other side of the mountain, to sail beyond the edge of the known map, is not a product of rationality or scientific method. It is something older and stranger, something that was in us before we had words for it. Think about what our ancestors actually did. Roughly 60 to 70,000 years ago, a small group of modern humans in East Africa made a decision, not a planned, rational decision, but a slow drift driven by curiosity and necessity to walk out of the continent, to cross into territory no human had ever entered. They crossed into the Middle East, into Central Asia, into Europe, into the cold tundra of Siberia. They built rafts and crossed open ocean to reach Australia tens of thousands of years before the invention of writing, using tools made of stone and bone. They reached the Americas, crossing from Asia across the Bering Land Bridge, and walked all the way to the southern tip of South America. A journey of roughly 20,000 kilometers on foot. No survival algorithm explains that. No straightforward calculation of resources and risk justifies crossing an open ocean on a raft made of reeds toward a horizon that offers no visible reward. Something else drove them. Something that was less about reason and more about need. The need to know what was there. That same need is alive in us right now. You feel it when you look up on a clear night and see the Milky Way arching overhead. That faint shiver that is half terror and half longing. You feel it when you hear that there is a rocky planet orbiting the nearest star, and your first instinct, before you even think about the obstacles, is, I want to know what's there. That instinct is not naive. It is not unscientific. It is the engine that has driven every major discovery in human history. It is the thing that put telescopes in orbit and probes beyond the solar system and footprints on the moon. It is older than civilization and more powerful than any single institution or government or crisis that has ever tried to extinguish it. And here is something worth holding on to. The people who will eventually design the first real interstellar mission, the engineers who will build the laser arrays and the fusion reactors and the sail films, many of them are alive right now. Some of them are young. Some of them are watching videos like this one, asking exactly the kinds of questions this video is trying to answer, feeling exactly the kind of spark that turns a curious person into a scientist or an engineer. The mission to Alpha Centauri will not be launched by a government or a corporation alone. It will be launched by a civilization that decided, collectively, that the question was worth answering, that the distance was worth crossing, that the stars were not just beautiful to look at but worth reaching toward. There is a concept in the history of exploration called the overview effect. It was first described by the writer Frank White in 1987, based on interviews with astronauts who had seen Earth from space. Almost universally, those astronauts described a profound shift in their understanding of what they were looking at. From orbit, the borders between countries are invisible. The atmosphere, the thin shell of air that contains every breath ever taken by every living thing in the history of our planet, is shockingly, frighteningly thin. The ocean and the land and the clouds all blur into a single, fragile, jewel-like object hanging in absolute darkness. Every astronaut who has experienced it describes something similar, a sudden, overwhelming sense that the divisions we maintain on the surface, nations, religions, ideologies, are arbitrary and small. that the thing we share, the planet itself, is precious and singular and irreplaceable, and that the vastness outside it is both terrifying and, in some deep way, an invitation. Imagine the overview effect from Alpha Centauri. Imagine looking back at the sun, our sun, as a faint point of light, indistinguishable from any other star in a sky full of stars. Imagine the Earth, and everyone who has ever lived on it, reduced to a fraction of a pixel, orbiting a dot of light 4.2 light-years away. What would that do to a human mind? We don't know yet. No human has ever seen it. But someday measured in decades or centuries depending on which technologies succeed, someone will, a human being, or the descendants of human beings, or perhaps a mind that thinks in ways we don't yet understand, will look back from the vicinity of another star at the faint point of light that is our home. And in that moment, the distance between the stars will not shrink. It will remain exactly what it is, 4.2 light-years of cold and silent void. But something else will change. Something about the way we understand our own place in the story. Something about what it means to be a small, warm, curious species on a small, warm, fragile planet, asking the oldest question there is, are we alone? And answering it not with hope or fear, but with evidence. In the next part of this video, we are going to talk about what actually needs to happen, practically, concretely, step by step, for the mission to Alpha Centauri to move from a dream into a plan. What are the milestones? What are the decision points? What does the roadmap look like from where we are right now to the moment a human-made object first enters another star system? And what role do you, yes, you, watching this right now, actually play in that story? Because you play one, whether you realize it or not. Let's get concrete. Because we've spent the last 8 parts of this video swimming in ideas. Extraordinary, mind-bending, genuinely important ideas. But ideas without a plan are just daydreams. And the story of humanity reaching Alpha Centauri is not a daydream. It is increasingly a project, a real, structured, step-by-step project with identifiable milestones, specific institutions working on specific problems, and a timeline that, while long, is not vague. So let's walk through it. Let's map the actual road from here to there. Not the optimistic version where everything goes right on the first try. The realistic version, the one that accounts for setbacks, for funding gaps, for political complications, for the kind of slow, grinding, unglamorous work that lies between a breakthrough in a laboratory and a functioning spacecraft in orbit, because that is what real exploration looks like. Not a single heroic moment. 1,000 moments, most of them invisible, most of them never making headlines, most of them happening in rooms you'll never visit, and every single one of them necessary. Milestone 1, proving the sail. This is happening right now. The materials breakthroughs from Brown University and TU Delft in 2025 have demonstrated that ultra-thin reflective films can be manufactured at a cost that makes the Breakthrough Starshot concept economically viable. But a laboratory demonstration is not a flight-ready component. The next step is scaling up, producing sail films not in small research quantities, but in the square-meter panels that a real mission would require, testing those panels under simulated laser illumination, verifying that they perform in vacuum conditions with the reflectivity and heat resistance the models predict. This work is happening at several institutions simultaneously. It is not glamorous. It involves a lot of failed samples and revised fabrication parameters and incremental improvements measured in fractions of a percent, but it is the foundation. Without a sail that works, nothing else matters. Realistic timeline for a flight-ready sail material. Somewhere between 10 and 20 years from now, assuming current funding levels and research momentum are maintained. Milestone 2, building and testing the laser array. This is the hardest engineering challenge in the entire Breakthrough Starshot concept, and the one that will require the most money. a ground-based laser array capable of delivering the power needed to accelerate a sail to 20% of the speed of light, doesn't exist yet, not even close. The largest laser systems currently in existence are research facilities like the National Ignition Facility, which produces enormous pulses of laser energy, but was designed for a completely different purpose and cannot be repurposed for propulsion. A Starshot-class laser array would need to combine thousands of individual laser units into a single, phase-coherent beam, meaning all the light waves are synchronized perfectly, so they reinforce rather than cancel each other. Achieving that coherence across thousands of separate laser emitters pointed at a target moving at increasing speed is a problem that current optical engineering is approaching but hasn't solved at the required scale. The proposed site for this array is in a high-altitude desert location, possibly the Atacama in Chile or a similar environment where atmospheric interference is minimized. Building it will require not just technological innovation, but an international funding commitment on a scale comparable to large physics facilities like the Large Hadron Collider, which cost roughly $9 billion to build. Realistic timeline for a functional prototype laser array capable of accelerating a test sail, 20 to 30 years from now. A full-scale array capable of a real interstellar mission, 30 to 50 years, Millstone 3, the first interstellar probe launch. When the sail technology and the laser array are both ready, and assuming the Starship electronics have been miniaturized and hardened to survive the journey, the first actual launch of an interstellar probe becomes possible. This mission would be unlike anything humanity has ever attempted. There is no retrieval option, there is no course correction once the acceleration phase is complete. There is no mission control intervention if something goes wrong in transit. The probe either works or it doesn't, and you won't know which for 20 years. The launch itself would be extraordinary to witness. The laser array fires for roughly 10 minutes. During those 10 minutes, the sail accelerates from 0 to roughly 60,000 kilometers per second, 20% of the speed of light. For comparison, the fastest human-made object ever launched, the Parker Solar Probe, reaches speeds of roughly 200 kilometers per second at its closest approach to the Sun. Breakthrough Starshot would be 300 times faster. After the acceleration phase ends, the sail drifts through the solar system, passes beyond the heliopause, the boundary where the Sun's influence gives way to interstellar space, and enters the void between stars. For 20 years it travels in silence. No communication, no data, just physics carrying it forward at a speed no human-made object has ever reached. Then, 20 years after launch, it enters the Alpha Centauri system. It has roughly a day to conduct observations as it passes through at speed, capturing images, measuring magnetic fields, sampling the interstellar medium, attempting to characterize any planets in its path. Then it transmits everything it has collected in a tight beam back toward Earth. 4 years later, the signal arrives, and humanity hears, for the first time, from another star system, Millstone 4, the robotic orbital mission. The flyby probe tells us what the Alpha Centauri system looks like from a passing glance. But a glance is not enough. The next mission, more complex, more expensive, further in the future, would need to actually stop, to enter orbit, to spend years rather than hours studying the system up close. This mission requires either a far more powerful propulsion system capable of carrying enough deceleration fuel, or an ingenious braking mechanism using the destination star's own radiation or the interstellar medium. Several research groups around the world are currently working on both approaches, though neither is anywhere near ready for a real mission. The most promising near-term path to a decelerating probe is a combination of laser sail acceleration and stellar radiation braking, using the push of Breakthrough Starshot's laser array to get the probe up to speed, and then deploying a secondary braking sail as the probe approaches Proxima Centauri, using the red dwarf's own light pressure to slow it down from the front. The mathematics of this two-stage approach were published in a widely discussed paper by physicist René Heller and colleagues, and while the engineering challenges are substantial, the physics is sound. A probe capable of entering orbit around Proxima b and studying its atmosphere, geology, and potential biosignatures for years would be, without question, the most significant scientific instrument ever built. And the data it sends back about whether Proxima b has an atmosphere, whether that atmosphere contains biosignatures, whether there is any evidence of liquid water on or below its surface, would reshape human civilization's understanding of its own place in the universe. Realistic timeline for an orbital robotic mission, somewhere between 100 and 150 years from now, assuming the propulsion and braking technologies develop on the optimistic end of current projections. Milestone 5. The decision. This is the milestone that doesn't appear in engineering roadmaps, but is perhaps the most consequential of all. At some point, after the flyby data comes back, after the orbital probe confirms what it finds, after the telescopes have characterized Proxima b's atmosphere and the results have been analyzed and debated and understood, humanity will face a decision. Do we go ourselves? Not a probe, not a chip, not a robot. Us, human beings, in a crewed vessel, crossing 4.2 light-years of interstellar space to reach another star system. That decision will not be made by a single government or a single agency. It will be made or not made by a civilization, by the collective will of a species that has spent centuries building toward that moment, debating whether it is possible, arguing about whether it is worth it, grieving the people who dedicated their lives to making it conceivable. And the answer, yes or no, will say more about what kind of species we are than any single decision in the history of our planet. Now, here is something I want you to really sit with, because it changes the way this whole story feels. The timeline we've been discussing, 20 to 50 years for the first flyby probe, 100 to 150 years for an orbital mission, 200 or more for a crewed mission, sounds long. It sounds like a future so distant it barely concerns us. But think about the people who laid the groundwork for the technology you use every day. The mathematicians who developed the theoretical foundations of quantum mechanics in the 1920s had no idea their work would lead to the transistor, which would lead to the microchip, which would lead to the device in your pocket that connects you to essentially all of human knowledge. They were doing pure science, abstract, seemingly impractical, funded by curiosity rather than application. And now their work is inside every piece of technology you own. The engineers who built the first digital computers in the 1940s, room-sized machines that performed calculations slower than a modern smartwatch, were not building the internet. They were building a first step. They were adding a stone to a path that other people, decades later, would continue laying. You are part of that chain. Not metaphorically, literally. Every time you engage with a video like this one, every time you ask a question about how the universe works, every time you support scientific education or vote for politicians who fund research or encourage a young person in your life to pursue science or engineering, you are adding a stone to that path. You are contributing to the civilization that will eventually, if we are wise enough and persistent enough, send something to another star. There are specific things you can do that are more concrete than that, and I want to name them because vague inspiration without actionable direction is just noise. The Breakthrough Initiatives, the organization behind Breakthrough Starshot, publishes regular updates on the progress of its research programs. The scientists working on laser sail materials publish their findings in open-access journals. Organizations like the British Interplanetary Society, the Tau Zero Foundation, and the Initiative for Interstellar Studies hold conferences, publish research, and actively engage the public in the work of interstellar mission development. These are not secret programs hidden behind government classification. They are open, public, often underfunded efforts that benefit from public attention and support. If you are a student, particularly in physics, materials science, electrical engineering, or computer science, the problems described in this video are real, open, unsolved engineering challenges that will define the careers of the people who solve them. The sail material problem, the laser coherence problem, the starship electronics problem, the closed-loop life support problem. These are not abstract puzzles reserved for a special class of genius. They are engineering problems that yield to hard work, creativity, and the kind of clear-eyed persistence that comes from genuinely caring about the answer. If you are not a scientist or engineer, if your skills run toward writing or policy or education or art, the mission to Alpha Centauri needs you too. It needs people who can communicate why this matters to the public. It needs people who can build the political will that sustains long-duration research funding. It needs people who can create the cultural stories, the films, the books, the conversations that keep humanity's attention pointed toward the stars across the generations it will take to get there. Exploration has always been a collective project. The ships that carried the first navigators across open oceans were built by carpenters and rope makers and sailcloth weavers, not just captains. The mission to Alpha Centauri will be built by a civilization, not just a laboratory. Let me give you one more thing to hold on to before we get to the final part of this video. In 1977, NASA launched two spacecraft called Voyager 1 and Voyager 2. Their primary mission was to fly by the outer planets, Jupiter, Saturn, Uranus, Neptune, and send back images and data. That mission was considered complete by the early 1990s. But the Voyagers kept going. They are still going. Voyager 1 is now roughly 24 billion kilometers from Earth, farther than any human-made object has ever traveled, and it is still transmitting, still sending signals back across the void, still functioning after nearly 50 years on a nuclear power source the size of a car battery. The engineers who built Voyager 1 in the 1970s are mostly retired or gone, but their work is still out there, still moving, still reaching. The message they sent into the universe, encoded in metal and mathematics and the patient work of thousands of human hands, is still traveling somewhere in the dark between us and Alpha Centauri. Long after the people who built it have been forgotten, Voyager 1 is making its way slowly, impractically, magnificently. That is what it looks like when a species decides to reach beyond itself. Not all at once, not perfectly, but persistently, stubbornly, with the specific kind of hope that doesn't require certainty to sustain itself. In the final part of this video, we are going to bring everything together. We are going to answer the question we started with: how long would it really take to reach Alpha Centauri? Not just with numbers, but with meaning. We are going to talk about what it would feel like to actually arrive, what the sky would look like from Proxima b, what it would mean for the story of our species, and why, of all the questions a human being can spend their life thinking about, this one might be the most important. Let's talk about what it would actually feel like to arrive, not the data, not the scientific measurements, not the mission objectives checked off one by one on a clipboard somewhere, the actual, visceral, human experience of being the first living thing from Earth to enter another star system. Close your eyes for a moment, or don't. Keep watching, but follow this with me and imagine it. You have been traveling for years, maybe 20, if the antimatter drives work the way the engineers promised. maybe 50, if the fusion reactors pushed you a little slower than the models predicted. The ship around you has become the only world you know in any immediate physical sense. The hum of the life support systems is the sound of home. The recycled air, the artificial gravity, the carefully maintained light cycles that simulate the rhythm of days and nights. These are not inconveniences anymore. They are the texture of your existence. And then one morning, or what counts as morning on your ship, the navigation system alerts you. You are close. Close enough that the instruments are picking up detailed stellar wind data from Proxima Centauri. Close enough that the spectrographs are resolving the atmospheres of the planets. Close enough that the star itself, which has been growing imperceptibly brighter for years, now fills a significant portion of the forward camera view. You are there. You are actually there. What does the sky look like from the vicinity of Proxima Centauri? This is not a poetic question. It has specific, calculable scientific answers, and those answers are extraordinary. The first thing you would notice is the star itself. Proxima Centauri is a red dwarf, which means its light is redder and dimmer than our Sun. If you were standing on the surface of Proxima b, assuming it has a surface you could stand on, the star would appear roughly 3 times larger in the sky than our Sun appears from Earth, because the planet orbits so much closer in. But it would be dimmer overall, a deep, ruddy, almost orange-red disk hanging in a sky that, depending on the atmosphere, might be tinted in colors nothing like the blue we know. Blue skies happen because nitrogen and oxygen scatter blue light more than red light. If Proxima b has a thicker or differently composed atmosphere, the sky might be orange, it might be purple, it might be a dark, dusky red at what passes for noon, with the star casting long, warm-colored shadows across whatever landscape lies beneath. And at night, if the planet has a night side, which depends on whether it is tidally locked, meaning one face permanently toward the star and one permanently away, the sky would contain something no human eye has ever seen from the ground. A bright star, not the brightest object in the sky. The star Proxima Centauri still holds that title from its own system, but a bright, steady, yellow-white point of light that is unmistakably different from the others. That light, slightly more than 4 light-years away, is the Sun. That is our Sun, the star our entire civilization was born under. The light that grew the first forests, warmed the first oceans, powered the first photosynthesis that eventually, through billions of years of biological complexity, produced the eyes you are reading these words with right now. From Proxima b, our Sun is just another star. That moment, that realization, when a member of our species first looks up from the surface of another world and finds the Sun among the stars, will be one of the most important psychological events in the history of our species. Not because of what changes in the universe won't notice, but because of what changes in us. There is a concept that the astronomer Carl Sagan explored in his final book. A photograph taken by the Voyager 1 spacecraft in 1990, when NASA turned the camera back toward the inner solar system from a distance of roughly 6 billion kilometers. In that image, Earth appears as a fraction of a single pixel, a pale blue dot, barely distinguishable from the noise in the image, suspended in a beam of scattered sunlight. Sagan wrote about that image with a kind of aching clarity. He said that every king and peasant, every saint and sinner, every creator and destroyer in the history of our species had lived and died on that dot. Every act of heroism and cruelty, every great love affair, every civilization that rose and fell, all of it happened on something so small it barely registered in a photograph taken from the edge of our own solar system. Now imagine that photograph taken from 4.2 light-years away. Imagine Earth reduced not to a fraction of a pixel, but to something below the resolution of any camera we could build, subsumed entirely into the faint light of its parent star. Imagine the whole of human history contained in a point of light so small and so distant that the instruments of our most advanced spacecraft can barely resolve it at all. What does that do to the question of whether our differences matter? Our borders, our conflicts, our centuries of violence over strips of land on a dot too small to see? And what does it do to the question of what we are reaching for when we reach for the stars? I want to tell you about a woman named Cecilia Payne-Gaposchkin. You may not know her name, but you should. In 1925, Cecilia Payne, a young British astronomer studying at Harvard, at a time when women were not even awarded degrees by Harvard, completed a doctoral dissertation that would turn out to be one of the most significant contributions to astrophysics in the 20th century. She analyzed the spectra of stars and concluded, using careful, rigorous mathematics, that stars were composed primarily of hydrogen and helium, not iron, not the same mix of elements as Earth. Hydrogen and helium, in quantities so vast they dwarfed everything else. Her thesis committee, all men, rejected her conclusion. One of them, a respected astronomer named Henry Norris Russell, pressured her to add a note to her dissertation stating that her result was almost certainly not real. She did. She added the note, published the dissertation and moved on. 4 years later, Russell ran his own analysis of stellar spectra and reached the same conclusion. He published it, received the credit, and is often cited in textbooks as the discoverer of stellar composition. Cecilia Payne was eventually recognized, decades later, for what she had actually done. The discovery that stars are made of hydrogen and helium is foundational to our entire understanding of stellar physics, of nucleosynthesis, of where the atoms in your body came from. It is not a minor footnote, it is a cornerstone. Why am I telling you this story in a video about Alpha Centauri? Because the road to the stars is paved by people whose names we often don't know, people who did the foundational work, who ran the calculations, who built the instruments, who asked the questions that didn't yet have answers, and who did it without recognition, without fanfare, sometimes without even being allowed in the room. The mission to Alpha Centauri will be built on their work, and on the work of people alive right now who will never see the mission launched, whose contributions will be absorbed into the collective knowledge of a civilization the way Cecilia Payne's discovery was absorbed, quietly, completely, without sufficient acknowledgement. That is how science actually works. That is how exploration actually works. Not a parade of celebrated heroes, but a long, patient, mostly invisible accumulation of knowledge and capability, passed from one generation to the next, like a flame passed from one candle to another until the whole room is lit. There is a calculation that I find more emotionally moving than almost any other in the entire field of interstellar exploration. It goes like this. The light leaving Proxima Centauri right now, at this exact moment as you watch this video, will reach Earth in 4.2 years. And the light leaving Earth right now will reach Proxima Centauri in 4.2 years. This means that if there is anything in the Alpha Centauri system capable of looking toward our sun right now, what it is seeing, the light that is hitting its detectors or its eyes or whatever sensory apparatus it uses, left our sun 4.2 years ago, it is seeing our past, and we are seeing its past. Everything we observe in the universe is, in this sense, a message from the past. The farther away something is, the older the message. When we look at a galaxy a billion light-years away, we are seeing it as it was a billion years ago. The universe to us is a kind of vast memory, a record of things that happened, delivered to us across distances so great that by the time the information arrives, everything has moved on. This is not just a poetic observation, it has a practical implication for any interstellar mission. When the first flyby probe reaches Alpha Centauri and transmits its data back to Earth, the people who receive that data will be receiving information about a star system as it existed 24 years before the signal was sent, and 20 years of travel, plus 4 years of signal delay, puts the observation roughly a generation in the past by the time it's analyzed on Earth. We will always be looking at the stars through the window of time. The universe does not offer us real-time information about itself. Every discovery is, in some sense, a piece of history. But here is the thing about history. It tells us what is possible, and what is possible in this universe turns out to be extraordinary. Let's talk about what Proxima b specifically might look like if it turns out to be habitable. Based on current modeling of red dwarf planetary systems, a habitable Proxima b would likely be tidally locked. One face of the planet permanently facing the star, bathed in constant reddish daylight, the opposite face permanently in night, frozen and dark. And between them, at the terminator line where day meets night, a band of permanent twilight stretching all the way around the planet like a ring, where temperatures might be moderate, where atmospheric circulation from the hot day side might bring warmth, where liquid water might collect in rivers or lakes or shallow seas. This terminator zone, sometimes called the habitable ring, is where many astrobiologists think life would most likely exist on a tidally locked world, not on the blazing day face, where the star's radiation beats down without pause, not on the frozen night face, where temperatures might plunge far below any chemistry of life, but in between, in the permanent twilight, where the light is always low and red and ancient-looking, where the star sits perpetually on the horizon, where the sky on the night side is always full of stars. Imagine standing in that twilight. Imagine the star, reddish, large, motionless on the horizon, casting long shadows across a landscape that might be rocky or sandy, or covered in something that functions like vegetation but looks nothing like the green we know. Imagine the air, if there is air, carrying the chemical signatures of whatever processes have been running on that world for 4 billion years. Imagine being the first human being to breathe it, or the first to know conclusively that you cannot. Either answer changes everything. We are, all of us, made of star stuff. This is not a metaphor that Carl Sagan invented for emotional effect. It is a literal, verified, scientifically precise statement about the composition of your body. Every atom of carbon in your cells was forged in the core of a star that lived and died before our sun was born. Every atom of oxygen in every breath you take was produced in stellar nucleosynthesis, the process by which stars fuse lighter elements into heavier ones. The iron in your blood was created in a supernova explosion, one of the most violent events the universe produces that scattered its contents across space, where it eventually coalesced into the cloud of gas and dust that became our solar system, our planet, and eventually you are the universe looking at itself. You are what happens when the atoms produced in stellar furnaces find a way, over billions of years, and through a process of unimaginable complexity and luck and persistence, to arrange themselves into something that can ask questions. And the question you are asking, that we are asking together, right now, is one of the most profound ones those atoms have ever managed to formulate. What else is out there? What other arrangements did the universe produce in its other corners across its billions of years of burning and cooling and colliding? Are we the only experiment that worked, or are we one of countless? In the next part of this video, we are going to sit with that question seriously. We are going to look at what the detection of life, or even of simple biosignatures, on Proxima b would actually mean. Not just scientifically, philosophically, theologically, psychologically. How would it change the way 7 or 8 billion human beings understand themselves and their place in the cosmos? What would it do to every religion, every philosophy, every framework of meaning that humanity has ever constructed? And what would it mean if the answer turns out to be no? If Proxima b is barren, And we look further and further, and the silence continues. Because both answers matter. Both answers are part of the story, and we owe it to ourselves and to the question to take both of them seriously. Let's say it happens. Let's say the flyby probe reaches the Alpha Centauri system, sweeps through at 20% of the speed of light, captures its data, fires its signal back toward Earth, and 4 years later, in a radio telescope facility somewhere on our planet, in the middle of an ordinary night, a computer flags an anomaly in the incoming data stream, a chemical signature in the spectroscopic analysis of Proxima B's atmosphere, a combination of gases that should not be there if the planet is simply rock and chemistry and nothing else, oxygen, methane, together, in concentrations that cannot be explained by geology alone. On Earth, oxygen and methane coexist in our atmosphere only because life continuously replenishes both. Left to chemistry, they react with each other and disappear within geological timescales. Finding them together in significant concentrations on a world 4.2 light-years away would be what scientists call a biosignature. Not proof, not a photograph of an alien, but a signal, a chemical whisper from across the void that says something is alive over there and it is breathing. What happens next? Not to the science, to us. This is the question that philosophers and theologians and psychologists have been quietly wrestling with for decades. And it is one of the most genuinely difficult questions in the entire landscape of what interstellar exploration means for humanity. Because the discovery of life, even microbial life, even something no more complex than a bacterium on another world, would be the single most significant event in the history of human civilization. Bar none. Think about every framework of meaning that human beings have ever constructed, every religion, every philosophy, every cosmology, every attempt by our species to understand where we came from, why we are here, and whether we are alone. Every single one of them was built on the assumption, sometimes explicit, sometimes implicit, that the question of life in the universe was either answered by our own existence or unanswerable. The discovery of life on Proxima b would not just add a data point to the scientific literature, it would restructure the question entirely. It would mean that life is not a singular miracle that happened once on one unremarkable planet in one ordinary galaxy. It would mean that life is something the universe does, something that happens wherever conditions allow, something that is, in the deepest sense, natural. And if life is natural, if it arises wherever it can, then the universe is not the cold, indifferent void it sometimes appears to be. It is in some meaningful sense alive, not conscious, not intentional, but generative, teeming, a cosmos that produces minds as routinely as it produces stars. Let's think about what that does to religion first. Because religion is where most of human civilization has historically looked for answers about ultimate meaning, and it deserves a serious engagement rather than a dismissive wave. The major world religions have responded to this question in very different ways. Some branches of Christianity, particularly those rooted in a literal interpretation of Genesis, have historically struggled with the idea that Earth might not be the unique center of creation. But other Christian theologians have argued for centuries that the existence of life elsewhere would not contradict the fundamental message of their faith, and would instead reveal the creative abundance of a God who did not restrict the gift of existence to a single world. In Islam, the Quran contains verses that refer to living creatures beyond the earth, and among his signs is the creation of the heavens and the earth, and the living creatures that he has scattered through them. And many Islamic scholars have long argued that extraterrestrial life is entirely consistent with their theological framework, even expected. Buddhism and Hinduism both operate within cosmological frameworks that have always described a universe of vast scale, populated across countless worlds and countless cycles of time. The discovery of life on Proxima b would, for these traditions, be less a disruption than a confirmation of what their cosmologies have long described. The point is not that religion would simply absorb the discovery without any tension or adjustment. Significant communities of people would face genuine, painful reckonings with beliefs they hold deeply. That deserves acknowledgement and respect rather than dismissal. But the broader picture, looking across the full spectrum of human spiritual and philosophical traditions, is one of surprising resilience. Human beings are extraordinarily adaptable in how they find meaning. We have reframed our place in the cosmos before. We moved from believing the sun orbited the Earth to understanding we orbit the sun. We moved from believing our solar system was at the center of the galaxy to understanding we live in the outer suburbs of one galaxy among trillions. Each time, the adjustment was painful for some and liberating for others. And humanity continued. Now let's think about what the discovery of life would do to the political and economic reality of interstellar exploration, because the shift would be immediate and profound. Right now, the argument for sending missions to Alpha Centauri has to compete with every other priority a civilization faces: climate change, poverty, disease, the infrastructure of daily human life, against those immediate, urgent, grinding realities. The case for spending vast resources on a mission to a star system that might be completely barren requires a certain kind of long-term vision that is genuinely difficult to sustain in the political cycles of democratic governments. But if the flyby probe returns data suggesting life, even the chemical hint of life, the political calculus changes overnight. Suddenly, the mission to Alpha Centauri is not a luxury. It is not a scientific curiosity funded at the margins by philanthropists and research grants. It becomes a civilizational priority. It becomes the project, the thing that transcends the political cycles, that survives changes of government and shifts of public opinion, that commands resources the way only the largest human projects ever have. The discovery of life on Proxima b would do to interstellar exploration what Sputnik did to the space race, except on a scale that makes Sputnik look like a spark. It would light a fire under human civilization that no subsequent generation could extinguish. Because once you know there is something alive 4.2 light-years away, the question of whether to go becomes almost unanswerable in the negative. You go. You have to go. The question is too important not to. But now let's sit with the other answer, the harder one, the one that deserves just as much thought. What if the answer is no? What if the flyby probe sweeps through the Alpha Centauri system and the data comes back clean? No biosignatures, no atmospheric anomalies, nothing that chemistry alone cannot explain. What if the orbital probe, a century later, confirms it? What if Proxima b is exactly what the pessimists feared, a scorched, airless, radiation-blasted rock, its atmosphere long since stripped away by the stellar flares of a violent red dwarf, its surface as barren and cold and silent as the moon? And what if we look further, at the next nearest stars, at the hundreds of potentially habitable worlds that next-generation telescopes will identify in the coming decades, and the answer keeps coming back the same way: empty, quiet, lifeless? What does that mean? This is actually the scenario that some of the world's most thoughtful scientists and philosophers consider the most unsettling possible outcome. Not the discovery of alien life, but the confirmation of its absence. The growing, evidence-backed understanding that in a universe of 2 trillion galaxies, containing more stars than there are grains of sand on all of Earth's beaches combined, the only life we can find is us. The philosopher Nick Bostrom, who has written extensively about existential risk and the long-term future of intelligence, has made a counterintuitive argument that has genuinely disturbed many people who encounter it. He argues that finding simple microbial life on another world, Mars, Proxima b, anywhere would actually be terrible news for humanity, not because of any danger from that life itself, but because of what it would imply about the Great Filter. If simple life exists elsewhere, then the filter, the barrier that almost no civilization gets past, is probably not the origin of simple life. It's somewhere further along the chain, which means it's probably ahead of us. Which means the thing that destroys almost every civilization that reaches our level of development is something we haven't encountered yet. Whereas if we look everywhere, we can look and find nothing. If the silence of the universe is confirmed as genuine, not just incomplete searching, then the filter is most likely behind us. We got through the hard part. We are one of the rare ones. And that means the stars, when we reach them, are genuinely ours to explore. The barren universe is not a tragedy. It is, in its own strange way, an inheritance. There is a third possibility that rarely gets the attention it deserves. Not simple microbial life, not complete absence, but something in between or beyond. What if the data from Proxima b doesn't show the chemical signature of simple biology, but something stranger? What if the atmospheric readings are anomalous in ways that chemistry and biology as we understand them cannot explain? What if there are structures on the surface detectable in the probe's imaging data that have geometries inconsistent with natural geological processes? What if the answer to the question of life on Proxima b is not yes or no, but something we don't have a category for yet? The history of science is full of moments where the universe presented us with something that our existing frameworks simply couldn't contain. Quantum mechanics, dark matter, the accelerating expansion of the universe. In every case, the initial response from the scientific community was some version of, "This cannot be right, let's check the instruments." And in every case, the instruments turned out to be correct. The universe was right, the frameworks were wrong. Any honest reckoning with the question of what we might find at Alpha Centauri has to hold open the possibility that whatever we find might be something that requires us to build new categories, new ways of thinking about life, about intelligence, about what the cosmos produces, not just an answer to the question we asked, but a question we didn't know we needed to ask. I want to come back to something personal, something that sits underneath all of this science and philosophy and speculation. You are alive right now, in this specific window of time when this question is transitioning from the realm of pure philosophy into the realm of investigation. For all of human history before about the 1990s, the question of whether other planets existed around other stars was not answerable. We had no tools. We could speculate, we could hope, we could fear, but we could not know. The first confirmed detection of a planet orbiting another sun-like star came in 1995. That was within living memory. There are people alive today who remember a world in which we did not know for certain that other solar systems existed. Now we know of more than 5,000 confirmed exoplanets. We have characterized the atmospheres of dozens of them. We have found rocky worlds in habitable zones around multiple nearby stars. We have built a space telescope powerful enough to detect the chemical fingerprints of alien atmospheres. We are building ground-based telescopes that will directly image nearby exoplanets in reflected starlight. In one human lifetime, the question of whether other worlds exist went from unanswerable to answered. The question of whether those worlds harbor life is now the frontier. And the question of whether we can reach them is moving for the first time in history from philosophy into engineering. You are alive at the beginning of that transition, not the middle of it, not the end, the very beginning. And beginnings are the rarest, most precious places to be in the arc of any story. In the final part of this video, we are going to bring every thread together, every technology, every discovery, every philosophical question, every human story we have told across these parts. We are going to answer the question at the center of all of it, the one that has been quietly driving every single sentence since the very beginning. How long would it really take to reach Alpha Centauri? Not with a single number, with the full, honest, awe-inspiring complexity of an answer that actually does justice to the question. An answer that holds the science and the uncertainty and the human meaning all at once. An answer that sends you away from this video looking at the night sky differently than you looked at it before. Because that is what this question deserves. Not a number, a reckoning. So how long would it really take to reach Alpha Centauri? With the technology currently sitting on launch pads and in research facilities and in the hands of the best engineers our civilization has produced, the answer is never. Not in any meaningful human sense. Voyager 1, our fastest long-duration spacecraft, is covering roughly 17 kilometers every second. At that speed, it would take roughly 73,000 years to reach Alpha Centauri. That is not a journey, that is a geological epoch. That is longer than modern human civilization has existed. Nobody is waiting for that answer, but that is not the only answer. That is just the answer if we stop, if we decide right now that what we have is all we'll ever have, if we look at the tools in our hands today and conclude that these tools are the final tools. And nothing in the entire history of our species suggests that is how this story goes. Here is what the realistic spectrum of answers actually looks like, laid out cleanly and completely for the first time in this video. With Breakthrough Starshot, the laser sail technology whose key materials barrier was broken in 2025, a probe the size of your palm could reach the Alpha Centauri system in roughly 20 to 25 years of travel time. Add the 4-year signal delay, and humanity could be receiving the first close-up data from another star system within 30 years of launch. If the engineering comes together on the optimistic timeline, that launch could happen within the next 30 to 50 years, which means the first data from Alpha Centauri could arrive sometime in the second half of this century, within the lifetime of people who are children right now. That is not a dream. That is a project with a budget, a team, a set of engineering problems, and a timeline. With nuclear pulse propulsion, the direct descendant of Project Orion, updated with modern microfusion technology, a larger robotic probe capable of actually decelerating and entering orbit around Proxima b, could make the journey in somewhere between 40 and 100 years, depending on the specific design. A mission launched in the 2100s could be returning detailed orbital science from the surface environment of another star's planet by the 2200s, within 10 generations of people yet to be born. With mature fusion propulsion, if the ignition breakthrough of 2022 at Lawrence Livermore develops into practical fusion engineering over the next 50 to 100 years, a crewed vessel of perhaps several hundred people could make the journey in 50 to 100 years. A generation ship, yes, but a small one, a focused one carrying not a civilization but a crew with a mission. The people who arrive would be the grandchildren of the people who left. They would know from birth what they were moving toward. And they would arrive with antimatter propulsion. If the impossible seeming production problem is ever solved, if the energy economics of antimatter manufacturing are cracked by some breakthrough we cannot currently predict, a crewed ship could make the journey in 6 to 20 years, a single human lifetime. A crew that boards in Earth orbit and steps off at another star while their hair is still the same color, and with something beyond all of that, with the Alcubierre drive or its descendants. If the exotic matter problem yields to physics we haven't written yet, the journey could take days, hours, a duration so short it would feel less like travel and more like crossing a room. These are not equally likely, they are not equally close, but they are all physically possible. None of them violate the known laws of the universe, and every single one of them was considered completely impossible by serious scientists within the last 100 years. So the answer to the question, how long would it really take, is not a number, it is a range. And where you fall on that range depends on a single variable that has nothing to do with physics or engineering. It depends on how much we want it. Not want in the passive sense, in the sense of wishing it were true, of finding it inspiring to think about late at night. Want in the active sense. Want in the sense of funding the research, building the institutions, training the engineers, sustaining the political will across the decades and generations it requires. Want in the sense of treating the question of whether humanity can reach the stars, not as a luxury item in the budget of civilization, but as one of the central organizing projects of our species. Because here is the thing that the history of exploration teaches us, over and over, without exception. The obstacles that look like physics problems almost always turn out to be will problems. The technology to do something extraordinary almost always exists, or is close to existing, before the will to deploy it does. The first ships to cross the Pacific were not built because someone invented a revolutionary new hull material. They were built because human beings decided the ocean was worth crossing and kept building ships until they found one that worked. There is a word in Portuguese, the language of a culture that understood ocean exploration better than almost any other in history, that has no precise equivalent in English. The word is saudade. It describes a kind of deep, bittersweet longing for something beautiful that is absent or distant, not grief exactly, not nostalgia exactly, but a feeling that sits in between. A love for something you have not yet reached, a homesickness for a place you have never been. I think that word describes something true about our relationship with the stars. When you look up on a clear night, when the light pollution falls away and the Milky Way spreads itself across the sky in a river of 100 billion suns, you feel something. You have always felt it. Every human being who has ever lived under a dark sky has felt some version of it. Something that is not quite sadness and not quite joy, but carries elements of both. A pull, a recognition, a feeling that the distance between you and those points of light is not just physical but somehow personal. That feeling is not an accident. We are made of the same material as those stars. The iron in your blood was born in a stellar explosion. The carbon in your cells was forged in a stellar core. The calcium in your bones, the phosphorus in your DNA, the oxygen in your lungs, all of it was produced in the hearts of stars that lived and died before our sun was born. The universe spent 13.8 billion years building the atoms that make you up. You are, in a very literal sense, the universe's way of looking back at itself. And saudade, that longing for the stars, might be the universe recognizing itself across the distance. Let me tell you about a thought experiment that I find more moving than almost any other. Imagining that somewhere in the Alpha Centauri system, on Proxima b, or on one of the other planets we haven't fully catalogued yet, or perhaps on a moon we haven't discovered, there is a form of life. Simple, maybe, microbial, something that doesn't think or dream or ask questions. Something that simply exists as life simply exists on Earth, in the deepest trenches of our oceans and the hottest volcanic vents, tenaciously, persistently, without agenda. That life has been there for billions of years. It emerged from chemistry the way our life emerged from chemistry, through a process we still don't fully understand, in conditions we can only partially reconstruct. It has survived the stellar flares of its violent red sun. It has found its margins, its cracks, its protected corners. It has persisted, and it has been 4.2 light years away from us for the entire history of life on Earth. For 3.8 billion years, for the entire duration of every living thing that has ever existed on our planet. It has been there, we have been here, and neither has known about the other. Think about that. Think about the loneliness implied in that image. Two pockets of life, each one the only living thing its own observers have ever known, separated by 4.2 light-years of silence for billions of years. And then think about what it means that we are the first form of life on Earth, possibly the first form of life in this region of the galaxy to have developed the capacity to close that distance, to end that silence, to cross the void and say, in whatever language science speaks, "We are here and we found you, and you are not alone, and neither are we." That is what this is really about, not the technology. Not the propulsion systems or the sail films or the laser arrays or the warp equations. Those are means, tools. The thing they are in service of is something far older and far more important. It is the oldest impulse in our species, the same one that walked our ancestors out of Africa 60,000 years ago, the same one that built the first boats and launched them into open ocean without knowing what lay on the other side, the same one that looked up at the moon for thousands of years and eventually, one July morning in 1969, put a human foot on it, the impulse that says, "I want to know what is there, not because it is useful, not because it guarantees survival, not because the return on investment has been calculated and approved, but because the question exists, and we are the kind of creature that cannot leave a question unanswered when the answer is reachable." So let's go back to the night sky one more time. Time to clear night. Get away from the city lights if you can. Lie on your back on the ground, on actual ground, dirt or grass. Something that connects you physically to the planet you are part of, and look up, the star you cannot quite see with the naked eye. In the constellation Centaurus in the southern sky, or rather the three stars bound together in a system your eye resolves as one faint point, is Alpha Centauri. It is the closest star system to our own. It is 41 trillion kilometers away. Light takes 4.2 years to make the journey, and somewhere in that system there is a planet, roughly the size of Earth, orbiting in the zone where liquid water is possible, sitting in the dark and the silence of interstellar space, 4.2 light-years from the nearest other world that we know of, which is this one, which is us. We don't know what is on that planet. We don't know if it has air or water or any form of life. We don't know if it is frozen or scorched or something in between. We don't know if it is the most barren rock in the galaxy or the most important discovery in the history of our species waiting to be made. What we know, what this video has shown you, is that we are not powerless to find out, that the tools to answer the question are either in our hands or within our reach, that the people working on this problem are real people, doing real science, making real progress right now today in laboratories and university offices and research facilities around the world. And we know that the first step, the flyby probe, the laser sail, the 20-year journey, the 4-year signal delay, is not a fantasy. It is an engineering project. A project that, for the first time in human history, we have the pieces to begin. The question at the center of this video was, how long would it really take to reach Alpha Centauri? And the truest, most complete, most honest answer is this: it depends on us. It depends on whether we choose to fund the research, whether we sustain the institutions, whether we inspire the next generation of physicists and engineers and mission designers to spend their careers on this instead of something easier and more immediately profitable. Whether we tell this story, the story of the closest star, the nearest world, the oldest question, loudly enough and clearly enough and compellingly enough that it becomes part of the shared project of our civilization rather than a niche interest for people who own telescopes. With the technologies closest to reality today, a probe could reach Alpha Centauri in 20 to 25 years of travel time, launched within the next few decades. The first data from another star could arrive before this century ends. With the technologies we are beginning to develop, nuclear propulsion fusion drives. Robotic orbiters could reach Proxima b within 1 to 2 centuries. Detailed science from the surface environment of another world could be in the hands of our descendants within 10 generations. With technologies we can describe mathematically but haven't yet built. Antimatter drives, advanced fusion. Humans could make the journey within a single lifetime. People alive today could conceivably still be alive when the first crewed interstellar mission launches, and with technologies we haven't imagined yet, because every generation has been surprised by what came next. Without exception, throughout the entire history of science, the timeline could compress in ways we genuinely cannot predict. All of this is real, all of it is grounded in physics. None of it requires magic or violations of natural law. It only requires us to keep going. You are part of this story whether you feel like it or not. Not because you are a scientist or an engineer, though maybe you are, or maybe you will be, or maybe someone you love will be, but because you are a human being alive at the moment when this question transitioned from philosophy to engineering. When the first materials for the sail were proven manufacturable, when the first fusion ignition was achieved, when the first rocky planet in the habitable zone of the nearest star was confirmed. You are alive at the beginning, and beginnings belong to everyone. So tonight, or the next time the sky is clear and the lights are low enough, go outside. Look south if you're in the northern hemisphere, look up if you're in the south. Find the faint smear of the Milky Way if you can. Feel the actual planet beneath your feet. Feel the air, the thin, precious, improbable atmosphere that clings to this pale blue dot by gravity alone, moving across your skin. And then look for the star, the closest one, the one with the planet, and know that somewhere, 4.2 light years away, that planet is sitting in its own darkness and silence, completely unaware that a small, warm, unreasonably curious species on a neighboring world has just spent the last 100,000 characters figuring out how to reach it. We are coming, maybe not today, maybe not in your lifetime, but we are coming because that is what we do, because the question exists and the question is reachable, and we have never been the kind of creature that looks at a reachable question and walks away. And speaking of reaching other worlds, if you thought getting to Alpha Centauri was intense, wait until you see the video on your screen. We explore what actually happens to the first humans brave enough to set foot on Mars. The truth is far darker than anyone tells you. Click it, you won't regret it.